This is the second of our videos summarizing the usage of our inverse trig functions. We want to give the exact value of each expression without using a calculator. In this example, we have cosine of 2 tan inverse of -1. Now, anytime we have an inverse trig function, that's going to represent an angle. So really what we have here is cosine of 2 times some angle theta. We're going to use our double angle formula to come up with an expression that we're going to be able to plug into. Now, we actually have three options of formulas for our cosine double angle. You can choose whichever one you like. I'm going to choose 2 times cosine squared theta minus 1. I'd be inclined to choose one of the two that involves just a single trig function and not the one that has both sine and cosine in it. So cosine of 2 theta equals 2 cosine squared theta minus 1. Remember that this is the same as 2 times cosine of theta squared minus 1. We're going to use this tan inverse of -2 to create a triangle. Then we're going to take the cosine value of the triangle we create and plug it in here for cosine and simplify our expression. So we have tan inverse of -2. Remember that tan inverse is only defined from -pi/2 to pi/2, so we're looking only at quadrants 1 and 4. Our tangent value of -2 is negative. Out of quadrants 1 and 4, tangent is negative in quadrant 4, so we know to create our triangle in quadrant 4. The tangent of this triangle is -2. I always like to think of it as a fraction. So tangent is opposite over adjacent. So our opposite side is going to be -2, and our adjacent side is going to be 1. We want the cosine value of this triangle. That's going to be adjacent over hypotenuse. So we'll have to do Pythagorean theorem to get the hypotenuse of this triangle. So our hypotenuse squared is going to be 1 squared plus -2 squared. We're going to get a hypotenuse of the square root of 5. So cosine of theta is going to be adjacent over hypotenuse. Now, personally, I wouldn't spend the time rationalizing this because I'm going to plug it in to this expression and clean it up. So I'd wait because there may not be the need for rationalizing once we plug it in and clean it up. This is going to become 2 times 1 over the square root of 5 squared minus 1. Squaring 1 over the square root of 5, we can just square the top and square the bottom of our fraction. So that'll be 2 times 1 over 5 minus 1. That becomes 2/5 minus 1. We get a final answer of -3/5. Let's try another one. This time we want to find tangent of cosine inverse of square root of 3 over 2 minus sine inverse of negative 3/5. Each one of these inverse trig functions creates an angle for us. So we've got an angle alpha and beta. So what we're really looking at is tangent of alpha minus beta. We're going to need to use our tangent difference formula here, which says tangent of alpha minus tangent of beta over 1 plus tangent of alpha times tangent of beta. We are going to create two different triangles, one for alpha, one for beta. We're going to pull the tangent value from each of the triangles we create and then plug it into this expression here and simplify. So I'll start with alpha. Cosine inverse is defined from 0 to pi, so we're looking at quadrants 1 and 2. Our cosine value of square root of 3 over 2 is positive, and out of those two quadrants, cosine is positive in quadrant 1, so we know that's where our triangle is going to be. Cosine is adjacent over hypotenuse, so our adjacent side is square root of 3, our hypotenuse is 2, and we'll do Pythagorean theorem to find our opposite side. So I'll call that side y. 2 squared is going to be equal to the square root of 3 squared plus y squared. So we're going to get y to be equal to 1. So tangent of alpha, right, it's going to be opposite over adjacent, 1 over square root of 3. And just like the last example, I would not rationalize this right away. I'd plug it in and then see. So we'll be taking this 1 over square root of 3 and plugging it in both these two places. Now we got to come up with the triangle for our angle beta. All right, so sine inverse, well, that's defined from negative pi over 2 to pi over 2, so we're looking at quadrants 1 and 4. Our sine value is negative 3/5. Out of those two quadrants, sine is negative in quadrant 4, so I know our triangle is going to have to be in quadrant 4. Sine is opposite over hypotenuse. So we're going to have our opposite side and our hypotenuse, and we'll do Pythagorean theorem to find that x side. We've got 5 squared equals x squared plus negative 3 squared. We're going to get 4. So tangent of our angle beta, opposite over adjacent, is going to be negative 3/4. And we're going to take this negative 3/4 and plug it in for tangent of beta. Okay, so we're going to get 1 over the square root of 3 minus negative 3/4 over 1 plus 1 over square root of 3 times negative 3/4. Well, I think I'm going to do a little bit of cleanup here before I address the complex fraction. Right, minus a negative on top is going to become plus. And down here we have a positive times a negative. That's going to be minus 3 over 4 square root of 3. We're left with a complex fraction that needs to be simplified. The way that we simplify any complex fraction, no matter what we're doing in math, is to multiply each individual fraction by the LCD of all the fractions. Now, maybe you haven't found LCD where there was a square root in the denominator. We do it the same way as we would if it wasn't a square root. If it totally freaks you out, then you could rationalize this 1 over square root of 3 first, and then plug it in, and then multiply through by a slightly different LCD to simplify. So, that's always an option. The LCD, right, we're always just looking at the individual denominators, and we want the product of the individual denominators. Our LCD is going to be 4 times the square root of 3. So we'll multiply each one by 4 square root of 3 over 1. The whole point of multiplying through by the LCD is to eliminate all the individual denominators. So all the individual denominators should cross cancel out. And we see these square roots of 3 cancel out, leaving us with 4 times 1, which is 4. These 4's cancel out, leaving us with a positive 3 times square root of 3. This first pair in the denominator doesn't have a denominator, so that's just 4 square root of 3. And then in our last pair, the 4 cancels and the square root of 3 cancels, and we're left with just minus 3. I'm okay with this answer as is. You could rationalize it by multiplying by the conjugate of the denominator, but I'm totally okay with this as an answer. In our next example, we want to write as an algebraic expression in terms of u. We don't want anything trigonometric involved. We're going to approach this the exact same way that we have our previous examples. This inverse trig function represents an angle. We're going to use this to create a triangle. We then want the cosine of that triangle. I like this question on a test. So sine is defined in, sine inverse is defined in quadrants 1 and 4. In the directions, it said that u is positive. So if u is positive and the 4 is positive, that means that we've got a positive here, so our triangle has to be in quadrant 1. Sine of this triangle is opposite over hypotenuse, so u is going to be opposite. 4 is going to be our hypotenuse. Cosine is adjacent over hypotenuse, so we'll have to do Pythagorean theorem to find this side, this x side here on the bottom. 4 squared is equal to u squared plus that x side squared. 16 equals u squared plus x squared. Subtracting u squared over, and then we'll take the square root. We know a square root property, plus or minus, emerges, but since we're in quadrant 1, we know that that x value is going to be positive. So this is going to be positive square root of 16 minus u squared. Because of the minus sign underneath of the radical, we can't break that up and do the square root of 16 and the square root of u squared. We just have to leave it as it is. Now that we have the third side of our triangle, we want the cosine of that triangle. Cosine of that triangle is going to be adjacent, square root of 16 minus u squared, over hypotenuse, which is 4. So let's talk about our calculator a little bit here. The inverse trig function keys on a calculator give results in the proper quadrant based on that pure definition of the inverse function. When the problem you're doing has given the inverse function already, all we need to do is pop it into our calculator. They're asking us to give our answer in decimal degrees, so make sure your calculator is in degree mode. And we're just putting this right into our calculator, cosine inverse of negative 0.133488816. And we'll get theta equals 97.671 degrees. In our next example, we're looking to find cotangent inverse of 1.7670492. Now our calculator doesn't have a cotangent button. So we need to do some algebraic manipulation before we can plug this into our calculator. If theta equals cotan inverse of 1.7670492, then that means that cotangent of theta equals that number. We know that cotangent is the reciprocal of tangent, so we can rewrite this left side 1 over tangent of theta. I'm now going to multiply both sides by tangent to get that tangent out of the denominator. I will isolate the tangent by dividing both sides by the 1.7670492. And that brings us to tangent of theta is equal to 1 over 1.7670492. And then to find theta, we can now do tan inverse of this fraction. All right, we got to manipulate it so we can use our calculator. Into our calculator it goes, rounding to the nearest thousandth of a degree. We get theta to be equal to 29.506 degrees. I really encourage you to be plugging all of these examples in your calculator to make sure that you're using your calculator properly. In our next examples, we want to use a calculator to give each real number value. Well, that means radian. If it says degree, it means degree. If it says real number, it means radian. So make sure you've switched your calculator into radian mode. Arc sine, right? We know we have that button right on our calculator, so we're just plugging this right in, right? Although most of our calculators say sine inverse like this instead of arc sine. Plugging into our calculator in radian mode and rounding to the nearest thousandth, we'll get y equals 0.960. And don't be surprised if you're getting smaller number with the radian. Usually radian measure are relatively small numbers. And in our next example, right, secant inverse, another one that is not on our calculator. So we're going to have to do some manipulation to get it so that we can plug it into our calculator. I'm going to do this one a little bit quicker. All right, so secant of theta is going to be equal to our number, blah, blah, blah. I'm not going to write out the whole thing. So then this becomes 1 over cosine of our number. I'm going to multiply both sides by cosine. And then I'll divide both sides by that decimal, giving us cosine equal to 1 over negative 1.287164. So that means that theta would be cosine inverse of this fraction, and this we can plug right into our calculator. Plugging into our calculator and rounding to the nearest thousandth, we get theta to be equal to 2.461 radian.